Hello everyone, welcome back to our discussion on chemical thermodynamics. In this session, we will discuss thermochemistry, the fundamental laws, enthalpy or heat associated in various chemical and physical processes, and stabilization enthalpies like resonance enthalpy or bond enthalpy. So, coming to thermochemistry that studies heat changes associated in various chemical reactions and physical processes like in burning of wood, that is your biopolymers are converted to carbon dioxide and water with the liberation of heat, and in physical process like melting of ice where solid ice is converted to liquid by absorption of heat. So, during a chemical or physical process, there can be two consequences with respect to heat. That is, it can absorb heat either or it can release heat. And those processes which take place by absorption of heat is called endothermic process, like photosynthesis and melting of ice. Photosynthesis takes in energy in terms of light, and during melting heat is to be supplied. And the other one, the process which occur with the release of energy, they are called exothermic processes, and during exothermic process energy or heat is liberated out like in wood burning or condensation. During endothermic process, energy is taken into the system. That means the surroundings lose its energy or heat to the system. So the surrounding temperature decreases or the heat is obtained by the system. Therefore, endothermic processes, the heat is positive, whereas exothermic process during which heat is liberated outward to the surroundings and therefore the surroundings temperature increase, the system lost its heat, therefore the heat associated in exothermic processes are negative. So enthalpy change during the endothermic process is denoted positive, whereas enthalpy change during exothermic process is negative. And heat absorbed or liberated during a process, during a chemical reaction, reflects in the formation of new bonds or breakage of bonds. Therefore, enthalpies of reactions are containing information on bond energies. We will see this soon. And now we move on to the fundamental laws of thermochemistry. The first one is Lavoisier-Laplace law proposed by Antoine Lavoisier and Pierre-Simon Laplace. They observed there the energy change accompanying any transformation, any chemical or physical transformation, is equal and opposite to the energy change in the reverse process. So you've got two processes. First one occurs in one direction and the other one is in the opposite direction, and the two enthalpies or energy changes associated are equal and opposite. For example, when water is converted from solid form to liquid form, the enthalpy associated is this much with a positive sign, and when the reverse occurs, that is when liquid water is converted to solid water, you can see there the enthalpy change associated during that process is exactly same as the previous one in magnitude but with negative sign. So this justifies the Lavoisier-Laplace law that energy change during a process is equal and opposite to the energy change in the reverse process. And now we move on to Hess law of constant heat summation proposed by Jamin Hess, and he says the energy change accompanying any transformation is the same irrespective of the process occurs in single step or in several steps. This can be demonstrated with this example. Here, carbon is combining with oxygen to form carbon dioxide in single step in this reaction, and the respective energy or enthalpy associated is this much. And the same conversion, that is carbon to carbon dioxide, can be achieved in two steps like this, where carbon first combines with oxygen to get carbon monoxide, and the carbon monoxide is then converted to carbon dioxide. So the first step, that is the formation of carbon monoxide, involves enthalpy change somewhere around 110 kilojoules per mole, and the second step, that is carbon monoxide is oxidizing to carbon dioxide, involves enthalpy change somewhere around negative of 283 kilojoules per mole. So the sum total of the enthalpies associated in these two steps is somewhere around 393.52 kilojoules per mole, which is very similar or close to the value in single step conversion of carbon to carbon dioxide. So this justifies the Hess's law there. Enthalpy change associated in a conversion or transformation is the same whether it occurs in single step or in several steps. Okay, now we see a reaction enthalpy. So when a set of reactants is converted to products, you've got certain enthalpies associated, and that enthalpy associated during this reaction is called a reaction enthalpy, and normally it is written with standard reaction enthalpy because the heat associated in a process depends on the reaction condition. So it is normalized or standardized to standard conditions of temperature and pressure. So reaction enthalpy, the standard reaction enthalpy is defined as the difference between the standard formation enthalpies of the products and standard formation enthalpies of the reactants. And standard formation enthalpy is that the particular chemical is formed from its pure elements at standard conditions. So this is how you define a reaction enthalpy and reaction enthalpy at standard condition. And the reaction enthalpy is temperature dependent. And temperature dependence of reaction enthalpy is demonstrated through another law which is called Kirchhoff's law. Let's see it. Here you've got a plot of enthalpy of a given substance with respect to temperature. You cannot really measure the enthalpy of a substance at a point, but what you can measure is enthalpy change during a chemical transformation. Anyway, if you plot enthalpy of a substance against temperature, you will end up in a graph like this, and you've got enthalpy measured at a given temperature T1, that is HT1, and at another higher temperature you have got this enthalpy value, that is HT2. So these two enthalpies are related through the specific heat capacity of the substance, that is enthalpy at a higher temperature is dependent, or that enthalpy at higher temperature is related to enthalpy at lower temperature through this change in specific heat capacity when the substance is moving from temperature T1 to T2. Okay, this generalization can now be reflected to reaction enthalpies. Suppose the substance here is a reactant in the given reaction, and for the product substance also you can have very similar plot, that is the enthalpy temperature dependence of this product substance. So at the given temperature T1 you measure a particular enthalpy for the product, and at higher temperature T2 also you have got new enthalpy HT2 for the product. And the difference in enthalpies of the reactant and product at that particular temperature T1 marks the reaction enthalpy at T1. Likewise, the difference in enthalpy between reactant and product at the temperature T2 marks the reaction enthalpy at T2. And if you extrapolate the equation here over to the reaction enthalpy or change in enthalpy during the reaction, we will end up in this, that is the reaction enthalpy or the enthalpy change associated in the reaction at the temperature T2 and enthalpy change associated in the reaction at temperature T1. These are related through the change in specific heat capacity between the substances reactant and product over T1 and T2 temperatures. So this generalization is called Kirchhoff's law. And Kirchhoff's law helps us to calculate reaction enthalpy at a given temperature if the reaction enthalpy at another temperature is known with the help of specific heat capacity values of the reactants and product at the two temperatures. With that, now we can move on to the concept of bond dissociation enthalpy. That is the energy associated in breakage of one mole of a bond to give the separated atom in gas phase. That is the standard bond dissociation enthalpy when you standardize it to 1 mole of the substance in the gas phase. So you have got a molecule like this, and when it is broken into gaseous atoms, like the hydrogen fluoride molecule is breaking into hydrogen and fluorine atoms. You know, of course, there is an energy difference. The molecule is possessing lower energy than the system of separated atoms. So when you go from the molecule to the separated atoms, you have an increase in energy. So the energy absorbed during that bond dissociation process is called bond dissociation enthalpy, and the process of bond dissociation is endothermic because energy is absorbed, or the molecule absorbs energy so that it can break into two gaseous atoms. And now the consideration is a resonance effect and resonance energy. Resonance effect is the stabilization effect in organic molecules containing conjugated system or aromatic system. You can see detailed discussion of resonance energy in my organic chemistry lecture series. And here this molecule, the benzene molecule, is resonance stabilized. Stabilization energy is calculated from the experimental values of heat of hydrogenation, and this is calculated based on a theoretical structure called cyclohexatriene, a theoretical counterpart of benzene. We will now see how to calculate the stabilization or resonance energy of aromatic systems. Here is the hydrogenation process. A hydrogen molecule is added across a double bond to get the new molecule which is hydrogenated, and the heat of hydrogenation for one double bond is estimated to be 120 kilojoules per mole. And now let's consider the energies associated in hydrogenation processes of various systems. Considering this monosaturated system or cyclohexene, the heat of hydrogenation measured as 120 kilojoules per mole, exactly matching to our assumption based on this calculation here. And for a system with two double bonds, cyclohexadiene, you've got 231 kilojoules per mole, similar to the value but a bit less because there is a degree of conjugation in this molecule and partly it is stabilized. And if you consider the theoretical molecule cyclohexatriene, you expect there are three double bonds, so 3 times 120 kilojoules per mole, that is, we expect 360 kilojoules per mole will be the heat of hydrogenation for this molecule. But the actual counterpart, the practical counterpart of this theoretical structure, benzene, when you measure the heat of hydrogenation for benzene, we end up in 208 kilojoules per mole, which is far less than this 360 kilojoules per mole, which is our calculation. To be exact, the two structures, the theoretical cyclohexatriene and the real benzene, differ in heat of hydrogenation by a value around 150 kilojoules per mole. And this energy difference corresponds to the resonance energy or extra stabilization energy due to resonance. Or in short, benzene, the resonance hybrid structure, is stabilized due to resonance effect associated with an energy of 150 kilojoules per mole. This is how we calculate the resonance energy by using the idea of heat of hydrogenation or enthalpy of hydrogenation. Okay, with that we are now closing this session. We have discussed the concepts of thermochemistry, the fundamental laws of thermochemistry, and how to use the idea of enthalpy change in reactions to understand the bond energy and resonance energy. And the next new thing to come in the new session is the second law of thermodynamics. We will discuss about spontaneous processes and randomness of the universe. Okay, thank you.